Hello. So now I'm just gonna teach some random number theory just to revise as well and share stuff as well. So let's begin. So mainly today what my plan is, I don't have my setup, so I'll just try to type. And first today we're mainly going to do with something called induction. Like this is very important for proving stuff. Okay. So like but we'll go a holistic way, not like a random this is the induction process and everything. The first thing that we should do is the well ordering principle. So it says that for every non-empty set of non-negative integers contain, so I'm also learning with you, so let's just go ahead with like that. So for every non-empty set of non-negative integers contains a least element, that is some element. So basically the logic is that let's say there is S, okay, so S has a lot of elements. So what I'm saying is that there will be some element like this element, let's say K. This K will be less than all B for all B not equal to K, and B belongs to S. Okay, so you can skip this line as well if you want, but yeah, so it just says that every non-empty set S will have some least element. Okay, I know this is very trivial now, so this is very trivial, this is obvious, but the later stuff will uh, come from this. Okay, so let's see, I'm just following Burton, so I'll just what do you call it, I'll just get the screenshots of the theorems because it's too hard for me to write it once more with the proofs as well. So yeah, so here let's try to focus on this one, I guess. So if a and b are very positive numbers, then there exists a positive integer n such that na will be greater than ab. Okay. So they are saying for some AB n less than AB. Yeah, so this is what we are saying is that let's be a contradicting person and let's say n A minus B is less than 0 for some case. Yeah, there will be some cases. Okay, then S is equal to, yeah, so then I can from this I can write B minus NA will be greater than 0, right? So so this B minus NA set will be always greater than 0. This is a non-empty set, this is the positive set, so this is comes under the well ordering principle. So let's say this says that so there will be some B minus MA which is the minimum value, right? So least element is this, so B, so but we can also find B minus M plus 1A right now, which is less than this because this B is positive, M plus 1 is positive, A is positive, this will always be less. So we can say that B minus MA is not the smallest element now, so this is a contradiction. So we can say that for this NA greater than B is not a statement, so this will not hold. So by contradiction there will always be some positive integer n such that NA greater than B. So like, yeah, that's the approach, kind of the main approach here. So let's get the, wait, let me just close this, I guess. Let me get the next thing, that is the theorem of first principle of induction. So yeah, so this is the thing. So the first principle of induction kinda states something like this. Okay, so let's S be a positive integer set, 1 belongs to S, and if K belongs to S, so does K plus 1. If this is true, then S will be the set of all positive integers 1 to n. Okay, not 1 to n, like for all positive integers 1 to infinity, I guess. So we can prove like that. My intuition, like, okay, so leave this proof for now. My intuition might be something like, see, so if it satisfies for 1 and if we show that a condition that is true for k means it will be true for k plus 1. So if it satisfies 1, it will satisfy 2. If it satisfies 2, it will satisfy 3. So using this thing, so we can kind of prove it satisfies for everything, right? So that's my logic. Let's read the proof. Let t be the okay, I'll just delete my proof because it might be dumb. So let me just delete it, I guess. Delete. Okay, I'm just writing this on a mouse. I'll have the writing pad soon. So whenever I have that, I'll use that. So t will be the set of all positive integers not in S. So int does not belong to S. Okay. So this is the thing. Yeah, and this is non-empty. Let's say this is non-empty. Sorry, Slack notifications. So yeah, by the well ordering principle, we are dealing with positive integers and it is not empty. Then t will have some minimum element by well ordering element, min element. So we denote this by a. So this is like a because 1 is in S. So a will be greater than 1. A cannot be 1, right? And so 0 greater than a minus 1 greater than a. Why is this? Okay. Yeah, so this at least has to be 2, right? So this will be 1. So it's going to be 3. If this is 3, then 2. Yeah, this works. The choice of a is the smallest member. A minus 1 is not a member of t. So why? The choice of a as such implies. So if this is the if this is the smallest element in t, then this cannot be in t, right? So this is in S, right? So, but S has a condition. If k belongs in S, so does k plus 1. So if a minus 1 belongs in S, so does. So if a minus 1 belongs to k, so does a. So that means what? A belongs to t and a belongs, ignore my shit handwriting, a belongs to S, which is not possible, right? Because t is the set of everything that belongs in S. So we can say that the set will S will have all the integers, right? So this t set will be empty, right? So all the integers will be in S. Okay, that's a good proof. So let's see if I can find a sum or something. I guess I can think that would be the best thing. Where's the second principle? I want to go to the second principle, I guess. Second. What the? Okay, wait. Yeah. So here is one sum. I don't think they have given any solutions. But let's try to do it on our own. Is we have to prove that typical formula by mathematical induction. Okay, this is very famous formula, as you know, right? So does 1 satisfy this? So that is the first question. So first thing is, does 1 satisfy this? So 1 square is equal to 1 into 2 into 1 plus 1 3 plus 1 plus 2 by 6. So 1 satisfies this. Okay. Now to prove that if k satisfies it, k plus 1 satisfies it as well. All right. So so how can I talk about this? Maybe like if k satisfies it. So let's say 1 plus 1 squared plus k squared is equal to k into 2k plus 1. My shit handwriting, but please ignore it for today. You'll get a good handwriting soon. By 6. Now if we add k square, k plus 1 whole square, right? Plus k plus 1 whole square, both sides. So maybe this will be 6 below here. So this will be what? K square plus 1. I'm breaking this down. 2k plus 1 plus k square plus 1 plus 2k, right? So this becomes what? 2k cube plus 1 plus 2k plus k square plus 2k plus 1 plus k square. Okay, so this becomes 2k square 2k cube plus 4k plus 2k square plus 1, so by 2 by 6. So can I break this as, so this should come, I think so this will come out as this k plus 1 cube, sorry, k plus 1 into k plus 3 plus into k plus 2. Does it come out like that? I have no idea. Did I fuck up the calculation somewhere, I guess? I might, by 6. So 2k cube exists. That's okay. How many k square are coming? This will be k square into 2. 2k square. Okay. Does 4k come? 2k. Okay, it's coming out as 5k, I guess. Did I do something silly mistake, I guess? Yeah, let's just, it should come like this. I don't know. Like, I did some calculation error, I guess. It should come like this. But see, k square is coming, and even the multiplication, it doesn't come out as 3. It's 2k plus 2k plus 1 plus 1, right? So it will be 2k plus, yeah, it should be 2k plus 3. No, did I forgot the calculation here somewhere. This is plus k. Oh, this will be into 6. My mistake. There, then it is correct. Then it's, I forgot. I fucked up this calculation. It will be into 6 here. So this one matches here. Not an issue. So this is how like you solve induction sums, I guess. So now let me find if the second principle of induction is given somewhere or not. So this is the second principle of we don't use this as much as the first one. Is this so basically if k is a positive integer, as that k belongs to S, then k plus also oh, we were using this thing as well. So we were using this same thing right now. We use the second principle only to solve this sum. The first one is like a bit more formal, I guess. The set concept comes in the first one, while this is the yeah. So this tells 1 to k belongs to S, where it just tells k belongs to S. So yeah, it's the same result only. It's like nothing different. It's just including more stuff. So it does not matter. And I think that's it for induction. Like this is the main concept behind induction. What happens? I don't think anything else is there. So I'll end it here.